All right. Good afternoon, everyone. How are you guys doing? Good. All right. So today I have some chopsticks for you, and I don't have any food, but you'll see why. We need some chopsticks.
Thank you.
You're welcome. So one each. Please don't break them, okay? Actually, the whole idea of this is going to be to break the chopsticks and to understand a little bit better about linear elastic fracture mechanics with the chopsticks. Can you pass one, please? All right. So don't break them, okay? I know it's very tempting to break them as soon as you get them, but don't. Okay. The last thing that we saw was about how to understand a little bit better a problem of a fluid-driven fracture. And this is not just some sort of open mode fracture that just include mechanics, but here we have also the influence of a fluid that is opening the fracture and it's exerting a pressure and that transforms into a stress on the wall of the wellbore. In order to understand a little bit better what is going to be the width of this fracture and what is going to be the stress at the tip of the fracture, we're going to use the theory of linear elastic fracture mechanics in order to understand that. And the theory of linear elastic fracture mechanics was developed by Griffith, and the most basic problem that Griffith tried to solve was a problem in which we have a fracture which is already exists within a medium, an infinite medium. Here I just make a rectangle because I don't have infinite amount of paper, but you should imagine this as an infinite medium. Inside we have a fracture, and outside, perpendicular to this fracture, we're going to have a minimum total stress, and inside the fracture is just a line right now with zero thickness. So I'm just drawing the pressure that will be inside the fracture. This one will have, let's just call it for now, just a pressure P. This fracture, in order to open, has to have a pressure which is larger than the far field total stress. And for that, this fracture, the medium in which this fracture is, it doesn't have any pores, doesn't have any permeability, any nothing. So the total stress is just going to be an effective stress. And as I was saying before, for this fracture to open up, the pressure inside the fracture should be larger than the total stress, because otherwise it wouldn't have enough support on the wall of the fracture in order to open up. All right. What we're going to do is to simplify this model, and instead of considering far field stresses and a pressure inside the fracture, what we're going to do is we're going just to consider what we said it's called a net pressure. And a net pressure is going to be the difference. I'm having problem with lengths of lines today. It should be smaller. The net pressure is going to be the difference between the far field stress and the pressure within this fracture. Sorry. I have problems with signs today. Thinking too much on the chopsticks. It's going to be the difference between the pressure in the fracture and the far field stress. So if this value is positive, that means that the fracture might open. If it's not positive, then the pressure in the fracture is not enough to open the fracture. Again, as I was saying before, we are assuming that this is a medium right now with no pores, so the fluid cannot go anywhere. All right? Good. So the solution of this type of pressure applied on a linear elastic and homogeneous and isotropic solid. So this is linear, this is elastic, homogeneous, which means that the properties are everywhere the same, and isotropic, which means that the properties are the same regarding on which direction you apply an action. The solution of this tells you that, and probably you remember this from project number 3 or 4, something like that, tells you that if you were to open a linear fracture or a linear crack, it would open up as an ellipse. That would be the shape. And this ellipse, let me see if I can get it right. It's going to be something like this. We're assuming that the fracture does not propagate. So here, this is the tip of the fracture. It will be this point where there is no propagation. And inside, we're going to have, as we said before, a pressure, which is a function of x, where this is the variable x, and this is direction y. Hopefully, you notice too that since this linear crack before was closed, now it's open, it displaced a certain amount from the center to the new position, and that's going to be a displacement in direction y, and in this case it's going to be a function of x. So for example, displacement here is some value, but beyond the tip it is equal to 0. And because of equilibrium in the here in the fracture, the pressure that we apply, and because we're assuming there are no pores, is going to be counteracted by a stress, which in this case, if I draw the stress in direction y, is going to be sigma yy. We are also going to put some notation in here. This distance c is what is called the half length of the fracture. Okay, so as I was telling you before, we can use this theory, and Griffith solved this problem that for a pressure that varies as a function of length. But now we're just going to see the problem for a pressure which is constant. Which is a lot simpler than when it varies with length. And the solution for this, Griffith found that the displacement in direction y, perpendicular to the fracture, at the fracture, and that's why this one is equal to 0, and depending on position x, is going to be equal to it's going to be proportional to the pressure, and here we're talking in terms of net pressure. So the higher the pressure, the higher the bigger displacement. Makes sense. Inversion proportional to something which is called the plane strain modulus, where the plane strain modulus is a function of the Young modulus and the Poisson ratio. And let me continue. I'll explain a bit about this plane strain modulus in a bit. And it depends on, lastly, the position. And this equation is valid inside the fracture. Let me zoom in a little bit more so you can see a little bit better. Okay. Probably you notice that this is the equation of an ellipse. So the displacement, it gives you that ellipse. Yes, Jack?
So in the graph, we mentioned that uy is only dependent on x. So why in this equation we have like two different?
Because I'm meaning that you can also find a displacement somewhere over here. We are tracking the displacement of the solid. And here I just make it equal to x because I'm meaning that y is equal to 0. That means on this line. Okay. And because of the condition of the problem, we are saying that displacement beyond the tip is going to be equal to 0. So for x equal or larger than c, this is going to be equal to 0. And already from this equation, we can get what is going to be the maximum width of the fracture. The width is going to be the sum of the displacement of the upper wall and the lower wall in this case. And for this particular case, for constant pressure, the width at the center of the fracture is going to be the maximum, and we're going to call that W naught, and that's going to be equal to what? What is going to be x here when at the maximum? 0. Going to be 0. Therefore, the width is going to be 2 times this, 4 times the net pressure times fracture half length divided the plane strain modulus. All right, so we have solved the part of displacement and width with constant pressure. Let's go to the second part. The second part is about what is the stress inside the fracture, on the wall, inside the fracture, and also outside. Let's go for the easy part. What is going to be the stress inside the fracture, at the fracture, for x equal or smaller than c? If you remember what we were saying before, here on the wall of the fracture, the stress, it has to equal the pressure, and just it's going to be a compression in direction y because you're pushing against the wall, so it's going to be just a compression, and it's going to be equal to the pressure. Positive compression. What about the stresses at the tip or beyond the tip? Well, here it's where it gets a little bit more complicated, and the equation is this. It's also proportional to the net pressure, but now it is like that. And what is going to be the value of sigma yy at x equal to c? No. At x equal to c, the denominator is going to be 0, and x is going to be c, right? So this is going to be what? All of this. We cannot divide by 0. And in the limit, this is going to approach infinity. And since we have a negative term here, this is going to be negative infinity, which means that at this place, we're going to have a tension, and it's going to tend to infinity. So let me, if this is compression positive, let's follow this convention, and this is tension, sigma yy is going to be, is going to tend to infinity. And at a distance of about, let's see, somewhere over here. Let me move it so I add one more thing over here that I think is going to be cool. Let me move it somewhere over here. Again, this one tends to negative infinity, but at a distance equal to 1.15 c, so 15% of the fracture half length, we're going to get the value of the net pressure. So at this point, it's going to be negative the net pressure. And as you get closer, it's going to get more and more negative. And let me add one more thing over here. So on this side is going to be compression. Inside the fracture, we're going to have a compression. Probably I'm going to add some color to make this a little bit better to understand. As soon as you get into the tip and closer to the tip, it goes to negative infinity. And because of this, we cannot use tensile strength criterion, because with this type of equations, we predict a tension which is infinity, and everything is less than infinity. Even if we have a tensile strength of 100 MPa, that's going to be less than infinity. So we cannot use tensile strength criterion for this. And in order to overcome this issue is that we use the stress intensity factor, and I'm going to write the equation again for that. Ki, and I'm going to explain also what the Roman number means, is going to be defined as the limit of, I'm going to explain what this R means in a minute too, of the product of 2 pi r, where r is the distance from the tip to whatever position you're looking at. And what this means is coming from r, or going to r to 0 from the right, because you could also come from the left, but this means from the right. So as you get in this direction, the limit of the product of a length times the product of stress at a position close to the tip. So now when you get to a product of stress times length, this quantity, this product, is not going to be in an undefined number anymore, because notice, the length tends to 0 and the stress tends to infinity. So when you make the math, unfortunately, we don't have time for this. But when you make the math, you can recover that this is going to be a final quantity, and for the case of constant pressure, this value is going to be equal to the net pressure times square root of pi times fracture half length. And this is going to be the constant pressure solution.
What is the again?
Stress intensity factor. As we mentioned in the previous lecture, when the stress intensity factor is higher than the stress intensity factor at which the rock breaks, which is called toughness, then the fracture is going to propagate. When the stress intensity factor is less than that number, which is a property of the rock, the fracture will not propagate. I'll talk in a minute about how to measure fracture toughness. Let me finish with this and tell you what is this number one. In linear elastic fracture mechanics, we have three modes of fracture propagation. There is mode 1, mode 2, and mode 3. The one we're looking at right now is the one which is called open mode. And now you can use your chopsticks, but don't break them, okay? Don't break them yet. So, number one will be the one in which, if I mimic this fracture, will be the one in which the walls open with respect to each other. And let me see if I can, okay, that's a little bit better. And this is called an open mode fracture because the two walls are separating, and in here I've had a fracture to propagate. Let me at the tip. As we said, we're going to have tension, and the fracture will open or will propagate by opening the two faces. So this is called open mode. And mode 3 and mode 2 are shear. Mode number 2 is shear in plane, and mode number 3 is shear out of plane. What does that mean? Okay, so open I just open this, opening the aperture. In plane shear would be an action in which I, for example, pull from this one in this direction and push this one in this other direction. So if you grab the chopsticks, will be like pulling one and pushing the other. You're going to create some tension at the tip, but if you can break it like this, I'm going to buy you dinner in this mode. You will see it's very difficult, but don't harm yourself, okay, in doing that. And mode 3 is going to be out of shear, and out of shear is this, that this opens, the fracture doesn't open in like that, separating, but it's like this. The two faces get out of the same plane, and also you create shear at the tip. Okay, so then number 1, number 2, which is difficult to show here in the images, and number 3. Which one do you think is the highest value of toughness? So now toughness will be the value at which the material would break. So KIC, or critical, that's why the C, critical stress intensity factor, will be the value at which the rock breaks, or K1C. Which one you think is going to be the smallest? K1C, K2C, or K3C? Just by doing the test that you are doing right now. Probably it would depend on the material. I mean, K3C, it looks like you can do the test just in a bit, but in general, K1 is the lowest. So critical stress intensity factor is a property of the rock, and it can be measured in the laboratory with, for example, the 3-point loading method. Or also, well, let me explain what a 3-point is. Basically, you get a sample, you make a notch, and you load it like this. And you can figure out by doing some calculations and computing stresses what will be the critical factor and what will be the critical force that will make this fracture to propagate. And another one is the semicircular bending, and this will be a 3-point bending or 3-point loading method, in which, and this is more popular for rocks because it's easier to core. You get the rock, split it in half, make a notch, and load it from the top. And you put rollers on the bottom that act as a reaction. But what we're going to do now is let's just run our test. First, as I was telling you, try to break it in mode 2, very hard, okay? Mode 3, probably you will be able to break it easily, but try to open in mode 1, you will see that probably that's the easiest. You can go ahead. Yes, Jack, I'm going to try to make it in mode 3.
Yeah. So for mode 2.
So actually quite strong in mode 3.
So
Yeah.
for mode 2, are we going to have a opening because it seems like it's mostly shear?
No, it's a shear.
Yeah,
Propagation of a shear.
Yeah,
Shear mode. No,
so
you don't need an opening.
yeah, so
The faces could be one next to each other.
okay, so we don't have a width, right?
You don't have a width, no. Correct, you don't have a width. So yeah, you can break it probably, you know what would be the easiest one? Probably if you grab it from the tips and you just pull it, it's automatically going to do a combination of 1 and 3. So you did the mode 3, right?
Yeah.
Well, you can do something very similar, but with rocks. And as I was telling you, this semicircular loading test consists of loading a rock which has a notch, and this, for example, if you go to Professor Olson's lab, you will see that he has some of these devices, and the equation here is that KIC is going to be proportional to the maximum load that you apply, the length of the notch, where this is A, and times a geometric factor, that it's about, it depends actually on the length of the notch, it depends on the distance, the radius of the sample, and it also depends on the spacing between the center of the notch and where the rollers are, but it's more or less about 5. And this one divided 2RL, where L is the width of the sample. So the long story short, you can measure this in the laboratory and you can use it to get to know if your fracture is going to propagate or not. Something very important that I want you to notice is that probably if you already, everyone already broke you didn't break them? Okay, I have more, but who wants more chopsticks? Okay, you have yours still.
Does it come
Okay.
with food now?
No, no. So only if you break them in mode 2. You have them? Stephanie, you broke them?
I didn't break them.
Okay. You're good guys over there? Okay. So something very important to notice here is that the stress intensity factor is proportional to pressure, which makes sense, but it's also proportional to the half length of the fracture. What that means is that if you grab again your chopsticks, also if you can break them by grabbing them very close to the tip and just pull them apart, also there is free dinner for you.
Oh, really?
Like less than 1 inch.
Less than 1 inch right here?
Yeah. Can you try that? Okay. So when the action is very close to the tip, now I'm trying to pull like very strongly, but I cannot break them. On the other hand, if you pull from them from a much longer distance, then it's going to be a lot easier to break them because the stress intensity factor is going to be proportional to the length of the fracture, or in this case, where you apply the load. So probably you can find the point at which you can break this. I don't know if we want to make a competition. Let's see. No. Okay, I got them at about 2 inches. You're cheating, Stephanie, or not?
No, I didn't.
You did it? That was a faulty chopstick, maybe. No.
Applying pressure on them for a while. So it's like I've been
So
creating Griffith fractures.
some fatigue, some subcritical loading. Okay. Well, the main concept here is that the longer the fracture, the easier it is to get to propagate a fracture, because intensity is going to be higher. If you have a longer fracture, it's much easier to propagate a fracture. Yes, Jack?
That's only applicable for mode 1, right?
No, also for modes 2 and 3. But we're talking about what will be the stress that is causing that. So instead of a pressure, you should have some sort of stress, a shear stress acting on the fracture.
So if we are talking about mode 2, does the radius matter?
So, well, for mode 2, the open mode, the analogy for this would be if you are opening a solid and pulling the two ends like that. In plane shear would be when you have a crack and you make this action. And out of plane shear would be when this is a little bit more difficult. is when you do something like this. And you pull in this direction and in this other direction. No, I got it wrong. Oh no, that's okay. So the further away you have your action, in this case we'll be having it further away in this direction, or in this case it will be having further away from the tip, the bigger is going to be your intensity. But in mode 2, that would mean having them further away from the tip, in like this. Instead of doing something like this, it will be having the same thing, but at a longer direction, in this direction now. Okay, guys, we have an exam and we have to move on. So let's continue. All right, so now we know, and we saw how we can use linear elastic fracture mechanics in order to predict fracture width, and also in order to predict the intensity factor, and also to measure the toughness of the rock. Okay, so there is one more thing that we have to do before we are able to jump into a problem of hydraulic fracture propagation, which is going to be to determine fracture height. And I think we talked about this a little bit, but not much, especially in project number 1. There are going to be several controls on fracture height, but the principal one is going to be stress. And probably the secondary one will be the toughness of the rock in order to avoid fracture propagation as well. But let's talk first about stress. Imagine that we have a rock which is composed by layers, and here we have stiff rock, here we have a soft rock, and here we have a stiff rock again. And now let's add to this, in the far field, a homogeneous or a constant displacement or constant tectonic stress along the entire interval. Let me add some axes here to make this a little bit clearer. So in the far field, there is a constant displacement which results in a constant strain in direction x, which is the same in all intervals. And we have stiff, soft, and stiff rock. My question here is, what is going to be sigma xx as a function of depth? We're compressing something in direction x, which is stiff, soft, and stiff. Will the stress be the same along the entire interval? No, why not?
Because they have different stiffness, so they're going to have different response to strain.
Right. So if you remember the most basic equation of elasticities, stress is equal to Young modulus or stiffness times strain. High stiffness, more stress. Low stiffness, less stress. So this is what we were doing when we were building our models of stress as a function of depth. And if we have a stiffer rock, that means that we're going to have more stress. If we have a softer rock, we're going to have less stress. So if we measure stress as a function of depth, we're going to encounter something like this, that the stiff rock is holding a higher stress than the soft rock. And because of this reason, if you were to start a hydraulic fracture somewhere along this soft rock, it will propagate. Let's assume the sigma xx is the same in the entire interval. And let's assume that the minimum principal stress is in this direction, in direction 3. So the fracture will open as a plane perpendicular to this direction, and since stresses are the same as you go in this direction or as you go in direction y, this is going to start opening as what is called a radial crack. And when it gets to the boundaries, it's not going to go up or down because the stress there is higher than here. The fracture is going to try to always look for the position or the places where the stress is the lowest. So why would it jump to the next layer if it can continue propagating in this layer of low stress? And as a result of that, and the effect of stresses, this is going to be a first order approximation of your fracture height. In fact, it might grow a little bit more in order to balance the stresses here, but that's going to be minor compared to the effect of the stresses. As we were saying before, you can also take into account the stiffness of the rock, and if you get the toughness of the rock, if you get to a very tough rock with the same stress as a function of depth, it might stop there as well. But usually the first control for growth is going to be stress. And we're just going to limit ourselves to that right now. We're going to use stress as a function of depth as a control for fracture height. All right, so now that we have fracture height, and if we assume this type of geometry, then let me think a little bit about if I do this. Probably I'll do this down here, and at the center, we're going to be interested in telling what is fracture width. Also, if we look at how far the fracture goes, that's going to be the fracture length, and it usually goes by xf. And last, we just saw how to determine fracture height, which is going to be hf. And now with all of these, we're going to put everything together in order to determine what is going to be the net pressure required to propagate a fracture with a given geometry. because we have almost all the components. All right. The first model that we're going to see is called the PKN model, where PKN, the acronym corresponds to the last names of people that came up with this model. And we're going to, let me write that very quickly, Perkins, Kern, and Nordgren. What they did was to solve this fracture propagation problem, assuming that we have a more or less simple geometry of the fracture. What did you say, Stephanie? Yeah. Okay. So imagine that we have a wellbore. Out of this wellbore, we're going to imagine a vertical fracture. And this vertical fracture is going to grow into this direction. It's going to have a tip. The tip is going to be defined as the point in the fracture where the width is equal to 0. And as you get closer to the wellbore, the fracture width is going to increase. So let me draw a couple of those. Probably you can notice from this schematic too that this model is going to assume a constant height of the fracture. And as I was saying, you get closer to the tip and the fracture width narrows, and this should be symmetric. Let me try one more time. And something like this. And from this model, here at the center, you can compute what is the width of the fracture at any position in the coordinate x. So let's say x is going to start somewhere over here, and so therefore this is going to be the width at the position x, where the maximum width is going to be at the wellbore. As we were saying before, the length of the fracture, we're going to call it xf, or I should say the fracture half length. Fracture half length is xf. And probably the most important thing from the mechanical point of view to consider in this model is that what this PKN model assumes it is a state of plane strain in the plane perpendicular to the fracture. So if I take a plane perpendicular to the fracture, this plane is a plane of plane strains, which means that there are no displacements outside this plane. So the rock is not moving in this direction or in that direction. It just moved in direction. Let me complete this. It moves just in the plane YZ. Anywhere inside along the fracture, there is just movement in direction YZ. There is no movement in direction X. So there is no strain in direction X. There is just a strain epsilon YY, epsilon CZ, and epsilon YC, for example, but there is no epsilon XX. So this is just plane strain on this plane. So epsilon xx is equal to 0, and this is what is called plane strain. And whenever we deal with these problems of plane strain, we can simplify our equations, and that's why, I almost forgot about that, that's why we use a plane strain modulus. This is just a simplification of a two-dimensional model to 2 dimensions. There is no strain in the direction perpendicular to it. As you may expect, if you try to compress a solid, let's say in this direction, up and down, you let it expand to the sides, but not in the front and back, that's going to be a state of plane strain, and pushing a solid in this condition is going to be harder than with this plane strain condition is going to be harder than if you let the solid expand in back and front. So it's similar to the constraint modulus, but in the constraint modulus you don't let it expand in 2 directions. In plane strain you let it expand in 1. And instead of constraint modulus, we have a plane strain modulus, which is higher than the Young modulus. Okay, so in this PKN model, then the plane strain is in the plane YZ in this example. All right, let's see what we do with this. Probably we won't have time to go through everything, but let's see how far we go. Okay, first step. We use linear elasticity, and we calculate what is the width of the fracture at the center of the fracture. Notice that the width varies with the position in coordinate z. It's not the same to be here than to be in the middle. At the top and the bottom is equal to 0. So the fracture width as a function of x at the center of the fracture, assuming this type of solution, is going to be equal to this, and this is an equation that we already had before. You remember that the first equation that we solved for the Griffith problem was this one, the width, where now the pressure or net pressure is, the pressure is going to vary, is going to be higher at the wellbore than at the tip. At the tip, actually we'll assume that the pressure is 0, the net pressure, and at the wellbore is going to be some value. So this is going to be a variable. At each position, the fracture is going to be the same. So we assume it's constant at each position in x, z, but it varies as a function of x. So, and this is a fracture half length, HF divided by 2, and we also consider that constant, even if we are here at the tip of the fracture. So, all right, then we have the value of the net, we have the value of the width of the fracture. The next thing that we're going to do is we're going to use the equation of fluid mechanics for laminar flow and a Newtonian fluid that tells me what is the gradient of pressure for 2 parallel, actually not 2 parallel, an ellipsoidal aperture, and this is equal to this. depends on the viscosity of the fluid, depends on the flow rate at the position x.
So
64. That's a 64. Just a number. As we were saying before, this is related to the cube of the fracture width, and it's also related to fracture height. So again, for this one, this is flow through you can think as through a pore or through a cavity of elliptical shape, and with Newtonian fluid flow, Newtonian fluid, and assuming that there is no turbulence, so it's laminar. This is just an equation of fluid mechanics. Next thing that we're going to do is material balance. In material balance, basically we account for where the injected volume goes. Because injected volume, as we inject into the fracture, it can go into the fracture, and we'll call that V, but can also go into the porous medium. So now we're going to also expand this for a short time to consider the leak-off. So this is the leak-off volume. This is what goes in the fracture. Notice that when the fracture is open, it's going to take some volume. So even if there is no leak-off, you need volume inside the fracture in order to be open, in order to propagate. The leak-off volume, there are several ways of dealing with this. The simplest way is to say, utilize an equation like this, where we say that the leak-off volume is proportional to the area of the fracture times a given coefficient, which is a function of permeability and properties of the fracturing fluid. And this is going to be a function of time too. So for this type of linear fluid flow, it's proportional to the square root of time. But don't worry about that. We're not going to deal with this right now. The injection volume for a constant injection rate is just going to be injection rate times time. If you have something a little bit more complex, then this equation is not going to hold. And if we don't have any leak off, the injection rate is just going to be whatever goes into the fracture. One more thing, this injection rate it just accounts for one wing of the fracture. So the actual injection rate at the wellbore is going to be 2 times I. Yes. Okay, let me see how we're doing with time. I think we have time, but we're going to do this very quickly. With all these equations, you can tell now what is going to be the value of the pressure as a function of x, the width as a function of x, and therefore what is going to be the pressure in the wellbore, the fracture length, and the width of the fracture as a function of time, because now we have a time variable. And the way that you do this is by, let's put some numbers over here. This is equation number 1, equation number 2, equation number 3, and equation number 4. So if I take equation number 1, equation number 2, and I say that the flow rate in the fracture is going to be to the injection rate, which I'm going to assume constant, for one wing, then this equation dp dx, variation of pressure along the fracture, is going to be this, but now instead of qx, I can put injection rate. Instead of width, I can use this equation of width over here. And all of that to the third power. And I can simplify this. You see there are some values that this is going to be 8, so 64 divided by 8 is just going to be 8. And later, this is a very simple differential equation that I can put this dp on this side and bring the net pressure here, and x put it on the other side. So this is going to look like Pn as a function of x to the third times dp is going to be 8 mu I. I bring the plane strain modulus to the top. All of these are just constants as a function of dx. And once I separate that, I can integrate. Is this still a negative? Yes. But I wanted to put it outside the integral. So we're going to integrate this from Pn at the wellbore to Pn at the fracture tip, and this is the same. And the integral of this is going to be the net pressure to the fourth power. So net pressure at the tip to the fourth power divided by 4 minus net pressure at the tip to the fourth power divided by 4. What did we say was the net pressure at the tip? Equal to 0. So we're going to cancel that one. So net pressure at the tip is equal to 0. And here, this is just going to be a simple integral, and where x, this is going to be this time xf minus x at x equal to 0, and therefore that term is going to disappear. So I'm just going to have here the term for xf. And now, with this equation, I know what is going to be the net pressure as a function of the fracture length and as a function of the injection rate. So let's do
So it's positive or negative? So double negative is positive, right?
what
So double negative?
is a double? Why did I write double negative? No, it shouldn't be double negative. No, it shouldn't be double negative. Sorry about that. So as I was saying, from here we can get what is Pn at the wellbore, and using the equation, well, let's just go ahead and write it. It's just math. This is going to be all to the 1/4. This is going to be equation number, the last one was 4, right? So this one is 5. This is going to be equation number 5. If I put equation number 5 and equation number 1, let's see what was equation number 1 like. Equation number 1 is the width of the fracture, and now we have what is Pn at, so this is the width as a function of the length, variable x, and therefore the width at the wellbore is just going to be what we have in here, or this, times that. So this is going to be equal to 512. This is just math again, combining the first equation and the one that we just got from integrating. And now we have net pressure at the wellbore and width at the wellbore as a function again of injection rate and fracture half length. All right, we need one more thing because we still don't know what the fracture half length is as a function of time. So in order to do that, in order to get that equation, we are going to use just some basic geometry, and by doing just some basic geometry, we'll find out that the volume of the fracture is going to be equal to the length, half length of the fracture times the height of the fracture times the average length, where the average length for this elliptically shaped fracture is going to be equal to pi over 5 times the width at the wellbore. And bringing again mass balance and assuming that all the injected volume goes into the fracture, so injection rate times time, we can calculate that the fracture half length is going to be equal to, from combining this one and that one, is going to be equal to this. All right, so now we have an equation for fracture length as a function of injection rate and as a function of time. And again, for this assumption, you have to assume what is the that you have a constant injection rate. Okay, this thing is actually this equation over here. We know what that value is. So now in these equations, I can replace what is going to be fracture half length by this amount, and I'm going to obtain the final equations of the PKN model that are going to tell me what is fracture half length as a function of time this is just a numerical value. It has pi in it. And here I'm just putting all the equations together. So we have fracture half length as a function of time. Here we have net pressure at the wellbore as a function of all the variables plus time again. And last, the width at the wellbore as a function of time. And what these equations tell you is that as time increases, of course, fracture half length is going to increase. The increase is not linear, but it's to 4/5. So it's something like that. The second equation tells you that as you inject with constant rate as a function of time, the net pressure is also going to increase, but it's going to increase less steeply, to proportional to the power of 1/5. And that makes sense. The net pressure should increase because every time you are opening a bigger and bigger fracture, and you're flowing more and more fluid into a fracture. And the last equation also makes a lot of sense, tells you that the width of the fracture at the wellbore, sometimes called W naught, is also going to increase, and is going to be proportional to the 1/5 of time. Okay, so I know this was a lot of equations, but I just wanted to show that this is a very simple model and that we can derive it in 15 minutes. The only thing that you have to do is assume a geometry, calculate what would be the width of the fracture for that geometry at the given pressure, which is variable as a function of x, calculate what is the profile of that pressure as a function of length in order to flow a fluid inside the fracture which has a given viscosity and through a cavity which is not constant but it is variable because it varies as a function of x, and just doing some mass balance to get to know how much volume it actually goes into the fracture and how much goes into the leak-off. For this particular model that we have over here, we assume that there is no leak-off. Probably we should write in here, this is no leak-off, and we also simplify a little bit the equations by assuming a constant injection rate. You do all of this and you do some math like what we did over here, and you get to these equations that we have right here that tell you what is fracture length, pressure, and width as a function of time. So that's everything that you have to do for this simple geometry. And with one more thing, probably that we didn't talk much about, is about fracture height. For this model, you have to tell the equations before what is fracture height. Well, all of these steps, determining fracture height, determining pressure, width, for a fracture is what goes inside a hydraulic fracture simulator. It's just that, but for something which is a little bit more complex. It is done with the same equations, but let me pull an example. Let's see. Okay. Okay, I'll come back to this one. I always forget which is the one that has the first part better explained. Yes. Frac Pro. So, okay. So this is the image I was looking for here on the right. In a fracture simulator software, you tell the software what is the profile of the rocks, what is the Young modulus, what is the stress, what is the mechanical stratigraphy, how stresses vary with depth. And what this software is going to do is, instead of assuming some shape of a fracture and some height of the fracture, is going to solve what is the fracture height and what is the fracture shape as you are injecting a fluid. But then it does all of what we did, but instead of solving analytically, it solves that numerically. Stresses around the fracture and also the flow in the fracture. But it's just putting all of these components together. Fracture height, which in this case it might vary as with fracture length, but then just fluid in the fracture and what will be the opening of the fracture as a function of pressure, and that's it. That's everything that goes into it. So if you put a few days of work, probably you could write your own fracture simulator. The advantage of this simulator is that they integrate very well petrophysical data, geological data, in order to have your model, initial modeling, which you work with. And probably here they have also complex fluid rheology, not only laminar flow or not only Newtonian fluid flow, but some other types of fluid flow that are non-Newtonian, and considering propan and a few more things. But the essence is what we just saw. And if you want to go a little bit more complex, this one is just for one fracture. I think this software also solves problems with several fractures, but coming back to the previous one, when you have now several fractures, fractures may start to compete with each other, and now we cannot assume anymore these conditions of far field stress or just one single fracture. You need to take into account what is the stress that the other fracture put into the medium that may be affecting. Let's say fracture number 2 started to propagate before fracture number 1, so that's going to have some effect in fracture number 1, so you need to take into account that. So you're going to have the simulation of multiple fractures propagating at the same time. At some point, even you may have that some fractures do not propagate at all because of the influence of other fractures. So this is a good example, let me zoom in over here, of how, for example, in our PKN model, we said the fracture height was the same everywhere in the pay. Well, in this case, it is not. It is the largest at where the injection is, but then it can find some places of low minimum principal stress, and it just goes through those layers instead of propagating through the entire formation. Something that probably would be nice to tell now is that fracture height is going to depend also on your net pressure. The fracture in this case is going to stay in a layer as long as the distance between this and that is higher than the net pressure, which means if I have a small net pressure, let's say somewhere from here to here, very likely the fracture just will stay in this location. But if at the wellbore, close to the injection point, as we were seeing, the pressure is going to be a lot larger than at the tip, probably at the wellbore, as the fracture gets longer and longer, the net pressure might overcome this initial stress difference, and now it might propagate into layers where it couldn't before, because now the pressure is higher at the injection point. And that's why you see over here in these fractures that the fracture tends to be covered a higher length in the vertical direction close to where it's injected opposite to the tips. That's because the net pressure at the injection point is a lot higher than at the tips. All right, so I think I have just one more example that could clarify this a little bit more. And this is, you will find an explanation of all what I said in, let me find it. Okay, here. Here, about how, this is something we already did, how we build these stress logs with VP, with VS, our tectonic strain, we calibrate it to measurements from the field, and we get this local minima of horizontal stress where the fracture will likely stay as long as the net pressure is not higher than that stress difference. And when you put all of these together, you can predict what is going to be the fracture height and the fracture width along this heterogeneous interval. So again, this modern hydraulic fracture simulator is going to solve all of this numerically, and it's going to give you widths and fracture lengths that are not constants along the direction of the fracture, but they can be variable. But that's everything into it. Okay, we're running out of time. I would just like to mention briefly that what we saw is just one model. There are two other models, analytical models that are helpful to predict net pressure, fracture length, and these are the KGD and the radial models. The KGD model, it's a model in which it's a little bit difficult to see here, so I'm going to do it over here. The KGD if this is your wellbore, the KGD assumes constant width along the fracture height, and therefore if you were to cut this fracture with horizontal planes, they will look all the same. question for you. What do you think is going to be the plane of plane strains in this particular model, where this is X, Y, Z? So this is going to be the width at the wellbore, and it's just a constant in the horizontal planes, in the plane Y, X. So in these planes, if we were to cut it with the horizontal plane, that's a plane of plane strains, YX. And you do again the same assumptions: constant injection rate, Newtonian fluid flow, no leak off, net pressure at the tip of the fracture equal to 0. And you will also find equations that tell you what is the fracture length as a function of time. I'm not going to write all of this. You can find the equations in my notes. The width of the fracture at the wellbore as a function of time, and the net pressure at the wellbore as a function of time. Something that I'd like to highlight here is that for this particular model, you predict that net pressure decreases as a function of time, which kind of, that does not make a lot of sense for, or it's not what we observe in the field. And because of that, and also because of the geometry, what we assume, usually this KGD model, and this is something very important to remember, is used to model short fractures. And what is something short? In this one, also the fracture height is constant. A short fracture would be a fracture for which the fracture half length is less than its height. And a long fracture, a PKN, like a PKM model, is used to model long fractures, will be a fracture in which the fracture half length is larger than the height. So usually this KGD model would apply better to model fractures, for example, for a leak-off test. But if you are doing completion with long fractures, the PKM model is going to work better for that. And one more thing over here I'd like to highlight is that there is a third one, which is a radial model. In the radial model, now there is not a constant height, but the fracture grows in the same direction, in this direction, than in this direction. So this direction horizontally and up and down. And it grows like an axisymmetric circle, or this is also called the penny shape fracture. So I think I just need 5 more minutes, but I need to upload this video. So then last one, I'm not going to make the drawing. It's also called the radial model or penny shape fracture. And for that one, you can also get these equations of fracture half length, width at the center, and net pressure at the center. Those all are going to be analytical solutions. All right, guys, I think we are on time to stop. So I'm going to upload my notes up to today, so you have them for the exam on Monday. And I already uploaded the practice exam. And also I'll try to get on your homework as soon as I can. Okay? Yes?
Any final tips for the test?
No, because I haven't done it yet.
Okay.
So I have to think about that. But very likely, since we did not get to cover everything on hydraulic fracturing, probably it's going to be heavier on the side of plasticity. And also it's going to include what we didn't see for the first part that was supposed to be included, but we didn't get to, which was thermoelasticity. And what else? And chemoelasticity and all of that. So all of that is going to be, and viscoelasticity is going to be in the exam too, okay? No, or, no, yes, bring a calculator. Bring a calculator.
Is it going to be more theoretical or analytical?
It's going to be more theoretical. Yeah. And what do you mean analytical?
I just,
Like deriving, doing some integrals and derivatives? Probably some very simple derivatives, like derivative of, x squared or x, something like that.